Today, we're really happy to have Junle Jiang from the University of Oklahoma to give the BSL Seminar, and Kang Wang will introduce him.
It is my great pleasure to introduce our today's BSL Seminar speaker, Dr. Junle Jiang from the University of Oklahoma. Junle graduated in 2009 with a bachelor degree in physics from the Yuanpei College at Peking University, which is the best university in China. He then went to Caltech, where he worked with Professor Ladia Lapusta and Mark Simons, and got his PhD in geophysics in 2016. After that, he worked as a green postdoc fellow at the Scripps Institution of Oceanography in UC San Diego. He also stayed a short amount of time at Cornell before he joined the faculty in the School of Geosciences at the University of Oklahoma. Junle has a broad range of research interests in the dynamic processes of the Earth's crust, combining numerical simulation, space geodesy, and advanced geophysical inversion techniques. He has published quite a few very remarkable papers using physics-based numerical models to help understand some of the intriguing geodetic and the seismic observations along the fault systems in Southern California. And I think that will be part of his talk today. He's also one of the leading experts pushing the immersion of geophysical data in a probabilistic framework, which is also known as Bayesian immersion. And he has successfully applied the method to study the fault motion during different stages of an earthquake cycle with different data types, including seismic, geodetic, and the tsunami records. And the title of his talk today is exploring connections between microseismicity, aseismic slip, and large earthquakes in Southern California. And with that, I will turn it over to Junle.
It's my great pleasure to give this Berkeley Seismology Lab seminar. And so the topic of today is mostly includes what I've worked during my PhD and as a postdoc at Scripps, and looking at mostly the seismic crustal faulting processes in Southern California. So Southern California, probably well known that Southern California has lots of geological faults and earthquakes. But if you just look at the faults itself, here it's a plot of some of the major fault systems in the major faults in the San Andreas fault system. And we can see that there's a major traces from San Andreas fault, San Jacinto fault, El Sino fault, etc. However, if we just look at active microseismic activities in the region, it shows a different picture. So if here we plotted earthquakes as dots here, colored by their distance to individual geological faults, and you'll see that the patterns in seismicity in Southern California does give us some kind of important information. First of all, we see that seismicity are clustered in space, and also the concentrated seismicities in some areas at least delineate the kind of elongated features of faults. However, recent earthquakes really only provide partial information about faults, because we can see that there's large gaps of seismicity along San Andreas fault, and from which you cannot see from the previous figure. We infer about earthquake activity. We have collected a lot of information about earthquake activity from seismology. So what's shown here in the bottom is kind of a zooming view, a focused view on the Southern San Andreas fault and the San Jacinto fault, and plotted in a 3D perspective view with vertical direct dimension exaggerated. On top of these 3D fault geometry, I also plot the seismicity as dots with their color indicating their distance to the fault. So we can see a lot of these so-called on-fault seismicity are mostly occurring on the San Jacinto fault and only on a few segments along the Southern San Andreas fault, and most particularly the Parkfield segment. We also know about earthquakes, at least in the past, from paleoseismology. So the figure on the top summarizes about the historical as well as prehistorical earthquakes on the San Andreas fault and the San Jacinto fault, some of which from paleoseismology as well as from historical records. So what we know is that the Shalom, Carrizo, Mojave segments on the southern San Andreas fault has hosted the recent largest earthquake in Southern California, which is 1857 Fort of Horn earthquake with a magnitude 7.9. The southernmost San Andreas fault hasn't had an earthquake rupture for almost 300 years. So to understand, our study is really trying to understand what we can say about large earthquakes in Southern California. Now that we have these kind of different information from seismology, from the fault geometry and paleoseismology. So to understand the interplay of earthquakes, it will ultimately comes down to understanding interactions or the connections between small and large earthquakes, as well as aseismic slip that doesn't radiate seismic energy, but we know has been observed in a variety of different settings of fault zones. And ultimately, the potential interactions between these processes is governed by the conditions of the seismogenic zone, which include the contributions of the complex rupture dynamics during these events, subject to the controls of fault structure, as well as fault friction and rheology. So it's a complicated problems here. And my talk here only attempts to address maybe some of the relationship as in our studies. So mostly, I think I'll talk about the two parts in my seminar. One is, first part is about what are the earthquake processes that we can infer at the base of the seismogenic zone. This is more of a model-driven, model-based, simulation-based studies about how large earthquake can influence aseismic slip and small earthquakes. And in turn, maybe we can say something about large earthquakes using microseismicity patterns. This is about the deeper seismogenic zone. The second part will try to investigate what are the geophysical signatures of post-rupture faulting processes, specifically at Parkfield, and from which we'll shed some light about the information of the deeper as well as shallower seismogenic fault zones. So for the first part, I'd like to start with what we also know about fault zones from field geology. Geological records of crustal faultings give us the direct constraint on the properties of fault zones and specifically its depth variations. And we know this is the famous example from the Punch Bowl fault. And it recorded highly localized brittle shear zones at seismogenic depths that has been exhumed nowadays. And we can see that where the fault zones have hosted major earthquakes, it has a principal slip surface that is very narrow and smaller than 1 millimeters. And is also seen in other exhumed major faults in the road. About the deeper part of the fault zones, we have less information, but but in a lot of the field examples, we know that there are relatively localized ductile shear zones at greater depths on mature faults. And a lot of these fault zones accommodate predominantly aseismic deformation over a probably wider monolithic zones of tens of 100 meters. So from these kind of geological records, we may come up with the idealized fault zone model. So here's the 3D fault zone model that we draw this, we produce a sketch for. Here, we are considering a vertical strike slip fault embedded in the fault zone bulk, which is subject to long-term interseismic loading. And due to the tectonic loading, earthquakes can initiate at the base of the seismogenic zone, which is marked in gray colors, and with the different circles indicating different sources or forms of fault heterogeneity. Earthquake can start at the deeper part of the seismogenic zone and propagates through the seismogenic zone and maybe toward also into some of the creeping parts of the fault zones. So here we refer to the deeper part of the fault zone as deeper creeping fault extensions. That's at least applicable on some mature faults and supported by a range of studies, including tectonic tremor, post-seismic deformation, as well as exhumed fault zone studies that we saw earlier. So if you just look at the base of the seismogenic zone and try to understand the depth-dependent fault behavior, in general, we know that the deeper part should be creeping or creeping aseismically at a certain rate, while within the seismogenic zone, because it produces earthquakes, so it tends to be locked between earthquake periods. Hence, it's mostly locked in the interseismic period. And between the locked and creeping zones, basic mechanical considerations will suggest that there should be concentrated interseismic stressing that's induced. And this kind of a concentrated stressing will be produced regardless of the level of fault heterogeneity. And if concentrated interseismic stressing occurs in the region where microseismicity is prone to occur, then it can produce concentrated microseismicity at the base of the seismogenic zone. But then we haven't really answered the question about what controls the style of faulting. Why some part of the fault tends to creep while others tends to undergo stick-slip motion, producing earthquakes. So over the past several decades, there is some laboratory-based understanding of frictional instability that can help us understand the depth-dependent faulting, the depth-dependent style of faulting. So this is the so-called rate and state frictionals, and it has been derived at relatively low velocity, slip velocities in rock mechanics, in friction experiments. The slip velocity usually are less than millimeter per second compared to the seismic range. Nonetheless, from the laboratory experiments, we have derived this phenomenological law, which has a simple elegant form here that describes that the coefficient of friction, which is the ratio between shear stress and effective normal stress, really is dependent on two variables, that is slip rate V and state variable theta, along with a few other friction parameters that describes the various processes which can be measured in the lab. When slip velocity is constant, we have a so-called steady state coefficient of friction, and steady state coefficient of friction only depends on slip rate as well as the friction parameters A minus B. So here comes the important concept. The most basic important concept in rate and state friction is that of the velocity strengthening versus the velocity weakening friction. Velocity strengthening is the situation where A minus B parameter is larger than 0. It describes the fault areas with such velocity strengthening properties will increase in their frictional strengths with slip velocity. Therefore, the fault area will undergo slow slip under slow loading. For fault areas with velocity weakening frictions, the friction will decrease or the frictional strength weakens with slip velocity. So seismic slip will be initiated in these fault zones if the slipping zone is large enough. So now we have this understanding of rate and state frictional properties and how that relate to frictional instability, then we can at least explain why some part of the fault, such as in the seismogenic zone, it is locked. We can explain that by velocity weakening properties, which can produce earthquake nucleation, hence starting an earthquake and making the fault areas locked between earthquakes. In deeper fault extensions, velocity strengthening frictional properties can explain why this fault area is creeping without ever producing seismicity. However, the reality is more complex. As we mentioned, rate and state friction, even though widely used nowadays, it is really derived from low velocity friction experiments. And there are a little bit of complexity in terms of fault behavior. because rate and state friction describes the conditions for earthquake initiation because it relates to the frictional instability conditions. However, once the earthquake started propagating, right, the condition of fault weakening would be different. If you just look at the fault behavior, and maybe the earthquake that started within the seismogenic zone can propagate deeper and penetrate deeper into the creepy regions, because even the deeper creeping faults may weaken dramatically during seismic slip rates. This kind of consideration is supported by almost ubiquitous observations of a variety of high velocity enhanced dynamic weakening mechanisms in laboratory rock experiments. One example of which is more based on basic physical considerations, although not fully kind of observed in the lab, is the shear heating induced thermal pressurization of pore fluids during seismic slip can weaken fault dramatically and perhaps facilitating the kind of propagation of faults from the seismogenic zone into the otherwise creeping fault areas. So this is a relatively simple considerations based on our current understanding of laboratory rock friction experiments, as well as some basic mechanical considerations of stress concentrations. So we incorporate those kind of ideas into developing numerical simulations of earthquake sequences and aseismic slip. So here we have two models using which we with which we explore the effect of the depth limit of earthquake rupture on resulting microseismicity patterns. So in these two fault models, we always consider 2D fault response in a 3D uniform elastic medium. The fault is vertical strike slip fault. And in these two models, we consider the same kind of transitions in terms of rate and state frictional properties, meaning that we always consider a velocity weakening fault zones indicated by this white rectangle in both models, surrounded by velocity strengthening areas colored in yellow. And we also consider dynamic weakening mechanisms that can control the propagation of dynamic earthquake ruptures. So that's the only difference in these two models, in which the first one, the dynamic weakening is limited in terms of its depth extent, perhaps due to some dilatant strengthening or other kind of strengthening mechanism. So the earthquake rupture will tend to be confined within the velocity weakening zone. But for the second model, we allow the dynamic weakening to go even deeper, facilitating the earthquake propagation into greater depths. In addition to these frictional properties, we assign small patches, as you can see in these two models, which indicate velocity weakening patches that can act as fault heterogeneity that favor the nucleation of microseismicity. So we have these kind of models set up, and we use a spectral boundary element method to model the spontaneous nucleation, dynamic earthquake ruptures, and aseismic slip coupled with the temperature and pore pressure evolution. It's developed by Lapusta and colleagues. So I actually will not show the direct results of a numerical simulation for these two models, as I will show that for a slightly more complex model later. But basically with this simulation, we can simulate large earthquakes and small earthquakes and their interplay, as well as aseismic slip in consistent modeling framework, and see the produced geophysical observables in these models. So here, what I show is essentially the spatial patterns of the co-seismic slip during large earthquakes, during one large earthquake, and microseismicity in these two models. So these two models, M1, M2 here, are put next to each other. And what's colored here are the co-seismic slip distribution during one large earthquake in each of these models. On top of, and these large earthquakes generally have magnitude 7 to 7.5. On top of these large earthquake slip distribution, I plot the smaller earthquakes using a circular crack model, assuming a 3 megapascal stress drop, so that you can plot maybe the equivalent rupture radius, rupture area for these microseismicity. for smaller earthquakes in these models. There are aftershocks that follow larger earthquakes, and most of the events occur prior to the larger earthquake, so consider them to be interseismic events. And you can see in the two models, the difference in the co-seismic fault slip distribution during larger earthquakes is that the second event has deeper slip that occurs below the transition of the velocity strengthening and velocity weakening zones. And in terms of microseismic activity, the first model has more active microseismicity, but the second model is devoid of concentrated microseismicity at depths in comparison. If you look at the temporal patterns in terms of how the depths of microseismicity evolves throughout the seismic cycle. So what's plotted here is the vertical axis showing the depths, and with the horizontal axis showing the time relative to the main shock. And for these two models, here, the black dots indicate individual earthquakes in the simulations. So the main takeaway is that we can see that the first model has much more active microseismicity throughout the seismic cycle, while the second model only have a few seismicity prior to a larger earthquake. We also have a red line here that's plotting essentially the boundary of the locked and creeping zones based on slip rate threshold. Here we can see the locked creeping boundary changes with time and correlated with seismicity. So from these models, we hypothesize that this kind of a seismic quiescence nowadays that's observed nowadays on San Andreas fault can be explained by deeper earthquake rupture below the seismogenic zone. So essentially, we use the second model in which deeper slip kind of removes a lot of the active microseismicity. Use this kind of model to explain the current observations of the Shalom, Carrizo, Mojave segments, while the first model may be more applicable to Parkfield, where we do observe concentrated microseismicity at the base of the seismogenic zone. So going further.
Junle?
Yes.
I have a question. So
sure.
In the simulations, do you allow an event to nucleate anywhere in the model? Or
in the simulation, the earthquake can nucleate anywhere in the model, yes. And the heterogeneity itself, it's a form of kind of encouraging the nucleation within these spots. Although we don't necessarily need these kind of circular patches because earthquakes can indeed nucleate at the rheological boundaries.
Okay, so you don't impose the nucleation geometry, I think is what you're saying.
I don't even impose the nucleation location, although the length of the nucleation, right, the nucleation size is determined by our chosen parameters for our chosen frictional parameters.
Okay. And you start off with a rough stress model, a heterogeneous stress model.
When we start the simulations, we apply actually a spatially uniform stress profile. But as the model evolves, as the seismic or aseismic slip evolve, the stress heterogeneity will be kind of naturally introduced, right? And arise as a result of these interactive processes. Right. But the model is generally uniform, except for these patches, which actually are not essential to demonstrate the effect of the deeper depth limit of earthquake slip.
And one last quick question. Do you ever see events nucleating shallow?
No, not in these simulations. That's partly because we do have these patches that kind of favors nucleation. So usually it starts at greater depths, and usually the stressing rate, because it is a half, I don't know how to go back. Oh, yes, because we have a free surface here. Near the free surface, the loading, the velocity weakening, velocity strengthening transition here undergoes lower loading compared to the down dip transition. So generally, nucleation is favored at greater depths. And I think it's consistent with the general observations that the earthquakes tends to start at greater depths. Okay.
Can I ask a quick question too?
Sure.
If you go back to your last slide, in these schematic stress versus step plots, you draw the stress
Oh,
in the creeping part,
that's why.
yeah, at a pretty high level. And when I think of the deep San Andreas, especially under Parkfield, based on what we learned from the tremors there, the absolute stresses and friction levels seem to be extremely low, and we envision very high near lithostatic fluid pressure. So I guess the question is, does it make a difference in the modeling? Kind of a secondary thing to consider.
It's a great question. Short answer is no, it doesn't matter. Here is the absolute stress level is a large uncertainty in these models, but what really matters is really the kind of stress variations here, how the concentrated stress kind of at the rheological boundaries that loads seismicity. So I don't think I've explained this slide, but maybe a little bit explanation that I answered that. So here we're showing you kind of schematics of what we expect the slip rate will occur. Should be low slip rate within fully locked zones and the transition into fully creeping regions. And in the simulations as we explored, this kind of transition in the slip rate always occurs at a finite zone. And it's in the top limit of this transition zone where the slip rate actually has the fastest variation, where the stress tends to, where the stressing rate is the higher. So that's why I draw this bump here, this peak here that indicates stress concentration that usually associated with the occurrence of concentrated microseismicity. Roland may be referring to the stress level in this red blue plot, maybe on the greater depths here. So whether the stress level, as I draw here, should it be higher than those in the locked zone or not? In this case, it actually doesn't matter. The stress level may as well be low, kind of within deeper part, maybe on the San Andreas fault. But what really matters is the stressing rate, because stressing rate is always highest at this up-dip transition between the locked and creeping zone. And it's the stressing rate that kind of controls the occurrence of microseismicity as long as it's within a velocity weakening zone. I don't know if I answer your question, Roland.
That's great. Yeah, thank you. Appreciate it.
Yeah, but it's a big unknown. So here, using the schematic, I guess I can demonstrate that in the schematic to argue that show that the interseismic geodetic locking depths, which is essentially an independent observable, right? So far, we have not talked about geodesy, and interseismic geodetic locking depths, which is usually inferred from the geodetic measurements of surface velocity across a fault zone. And this interseismic geodetic locking depth usually is a kinematic estimate. So it will not resolve this single parameter, it will not resolve the detailed variation in the slip rate with depths. Usually we'll get estimate of geodetic locking depths that's somewhere in the middle of the transition zone. So this geodetic locking depths, based on this schematic, it should be comparable to or deeper than the concentrated microseismicity at depths. And this is also seen in our models. So let's see, can we actually test the model with what we have observed for the San Andreas and the San Jacinto faults? So this is a compilation. It's a plot that's using the results from Smith Counter et al. 2011. The study kind of estimate the so-called seismicity cutoff depths, major segments of the San Andreas fault here on the top and the San Jacinto fault at the bottom. Seismicity cutoff depths essentially is the estimate of the depths above which maybe 95 or 99% of the seismicity occurs. So these cutoff depths corresponding to 90 or 99% of the seismicity cutoff, drawn here as orange and red lines. Geodetic locking depths measured using surface GPS measurements of the interseismic velocity. It has a larger uncertainty, so I show here as blue bands with the indicating the range of uncertainties for the geodetic estimate. So as I mentioned earlier, from our modeling, we expect that the geodetic locking depths should be comparable to or greater than the concentrated seismicity. And we can see from the figure here, at least for the Shalom, Carrizo, Mojave, and some of the southernmost San Andreas faults, the geodetic locking depths do tend to be deeper. And it's worth noting that a lot of the geodetic locking dips are estimated based on a half-space model. So it's highly approximated surface structure. And the use of half-space usually tend to bias geodetic locking depth estimates toward shallower values. So the actual effective geodetic locking depths may be even greater. So I think at least this kind of a current day available observations from seismicity cutoff depths and geodetic locking, it's consistent with our model predictions. However, there's some interesting observations maybe associated with San Jacinto fault. So we can see the Anza segment, the geodetic locking depth seems to be shallower in the seismicity. So that's why we investigate later on in the next study. So San Jacinto fault seems to be much more complex in terms of microseismic activities, and it's along strike variations in its behavior. So here, this is the figure on which we plot the seismicity and as dots, with some of the larger seismicity as circles correspond based on the circular crack model. Here, along each segment that you can estimate seismicity cutoff depths based on seismicity alone. So the seismicity hypocenter depth is around 14 to 18 kilometers throughout the segments. On top of the Anza seismicity gap, we've had geodetic measurements from INSAR and the GPS to measure the interseismic velocity field and the stress accumulation across the fault, from which you can derive the geodetic locking depth, which is about around 10 kilometers, and while accounting for the layered structure. So it's a good estimate for the geodetic locking depths, and we can see that it's much shallower than the seismicity hypocenter depths. And this also, this kind of anomalously shallow geodetic locking and deeper seismicity depths on the San Jacinto fault is also an outlier if you compare the seismic and geodetic observables for all the segments in Southern California. So this is in a compiled study from Smith County 2011. And we can see for a lot of the segments in the San Andreas and the San Jacinto fault, a lot of them have kind of generally geodetic depths and the seismic depths close to each other. And Anza is one of the major outliers in this case. And even if we can take into account the realistic subsurface structure in estimating geodetic locking depths. So that's how we want further develop our models, because we've seen that for this kind of a simple 1D layered models, we should expect a deeper geodetic locking depths and maybe shallower seismicity. However, the reverse is true for the San Jacinto fault. So what really happened? So we suggest that maybe something complex about some complex velocity weakening or velocity strengthening transition can produce this kind of a reversed result. So that's why we set out to explore numerical simulations. Here, we develop a new model in which we can still consider a vertical planar strike slip fault in 3D homogeneous elastic half space. Now, instead of just relatively sharp transition from velocity weakening to velocity strengthening areas, now we consider a wide transition in zones in which we consider a stochastic distribution of frictional properties in terms of A minus B values. So that some areas has positive A minus B values, facilitating stable slip, as other areas with negative A minus B values that tends to promote frictional instability. And the mechanism for these kind of heterogeneous frictional properties could be due to a variety of sources, such as structural complexity and fluids. And we have, this is something that we cannot address in these models, but we take these as an input to see the consequences of such a heterogeneous fault property distribution. So certainly this model is not the reality. So the question is really, can we gain some insights into fault zone processes at this greater depths using such idealized models? And we think we can. So this is simulation that we have performed using the model setup of heterogeneous rate and state frictional properties on the fault. So here, what I showed is it is the initial snapshot in a simulation in which we plot the slip rates on the fault, the logarithmic slip rates in color. Hence, the darker color indicate locked state, while brighter colors kind of correspond to aseismic or seismic slip rates. So we started at a snapshot in the simulation where microseismicity is just about to start at the middle of this heterogeneous transition zones. Oh, sorry. And also, I should note that some of the contours here really draw the kind of boundaries between velocity strengthening and velocity weakening materials. Start simulation, and you can see the variations in the slip rates. Here, a lot of the slip rates kind of, some of the bright reddish colors indicate the current microseismicity, while yellowish colors generally means it's aseismic slip transients that can propagate across this transition zone. And so far, we see a lot of slip occurs in the transitional zone before it nucleates within the larger velocity weakening and produce a system-sized earthquake rupture, along with propagating waves, which wraps around due to the periodic boundary conditions of this simulation. But after the earthquake, a post-seismic slip occurs surrounding the velocity weakening zones, and then the whole process generally recur, along with some of the complexities, especially in the heterogeneous transition zones. So here we are showing you some more snapshots that shows the seismicity, aseismic transients, and large earthquake can be produced in this kind of simulations. As in the end, if we just choose one of the large event in the simulation and the smaller earthquakes produced in the interseismic and post-seismic periods of that earthquake, as these circles based on circular quark model, and we can see that there's large variability in terms of the location, these microseismicity, and some parts of the fault segment tend to produce more seismicity than others. It's mostly determined, I think, not necessarily, it's largely controlled by the heterogeneous frictional properties that we have imposed in this model. So what we can do here, in order to compare the simulation with the models, what we do here is we can take a snapshot of the simulation over a multi-year period and then do a time average the fault slip rates on the fault. Here's the depth, showing the depth profile of the slip rates with low slip rates in the locked zone, with the transitional slip rates into the fully creeping zone. As we can see, there's a finite transition zone between the locked and creeping zones. And from these fault slip rate distribution, we can compute the synthetic interseismic velocity on the Earth's surface. So the fault parallel velocity plotted as a distance to fault will show these kind of a characteristic profile, which is the arctangent function, and which has been well described by simple dislocation models developed by Savage and Burford. So this kind of profile can be well described by this equation that shows you that the interseismic surface velocity depends on the long-term creep rate at Parkfield, as well as the location of the effective geodetic lock-in depths. So we can use the synthetic surface velocity profile from a simulation, do an inversion to estimate the equivalent geodetic lock-in depths for several consecutive time periods throughout the simulation. So this is the inversions for this particular time snapshot that shows you that there's a trade-off. Certainly, in general, we can find the best fitting parameters for plate rate and lock-in depths, but in general, there's a trade-off between the two parameters. So we can do that for the entire period of the simulation. So what's shown here on the bottom panel, we show the estimate of the geodetic lock-in depths, equivalent geodetic lock-in depths in these models, and how it changes throughout the simulation time. So we can maybe focus on some small part of this simulation where it shows one seismic cycle. We can see that the equivalent geodetic lock-in depth is generally higher sometime after the earthquake, because you are mapping some of the post-seismic slip into the estimate of a simplified dislocation model. And the geodetic lock-in depths kind of deepens with time, although sometimes it could be transiently higher because of some of the aseismic slip that occurred in these simulations. So in general, when we compare the seismicity that's simulated in these models and the equivalent effective geodetic lock-in depths in these models, we can reproduce deeper microseismicity and shallower geodetic locking. So we consider that we can reproduce what we observe successfully. So there are several recent studies by looking at strain meter signals and seismicity rates. So studies by Imbal, studied by Shaddocks in recent years, they all take advantage of strain rate estimates, and from which they can infer there has been abundant episodes of aseismic slip associated, potentially triggered by regional or fault-field earthquakes. So in some sense, our study kind of taking advantage of the time averaged GPS measurements, we have already inferred the occurrence of aseismic transients, and these are somehow can be independently kind of verified by these higher resolution measurements from strain meters. So, so these kind of models have been increasingly popular, I guess, in the earthquake communities. Oh, sure, go ahead.
So I can see that, so you put it to the stochastic layer to explain that sort of, deeper seismicity and shallow locking depth. So that what does mean the other area, we don't see such phenomena. It is a much more simple layer rather than we don't need a stochastic transition for like other Parkfield or other area, which is more like normal to me.
Yeah, well, this is design is kind of we kind of designed that for San Jacinto fault, which we can somehow conceptually attribute to the structural complexity. So it may not be applicable to Parkfield. I don't think we actually. I don't think
we don't need to do like a stochastic transition, which seems to me is much more like a naturally changing. It's much more reasonable. So, but other way around, the Parkfield it's much more simpler and nothing really stochastic transition.
Let me see. I'm trying to understand the question. In that, I don't think we need. I guess that we don't need to consider such a complexity and explain the phenomenon in Parkfield at the greater depths, right? Because there's seems to be a well-defined concentrated microseismicity streak at greater depths, and the geodetic lock-in depths. I think from the geodetic lock-in depth seems to be kind of agree with the seismicity cutoff depth. So there doesn't seem to be a kind of unexpected relation between the two. Right.
So, yeah, right. So the other question, thank you. Other question I have is so the first talk you are talking to a dynamic weakening or not, right? Model A, model B. So for the answer case, which one you are using? You are using.
So actually, it's a very good point. So in the second case, I actually do not use the dynamic weakening. So in some sense, you can read that we can use simple rate and state friction with these heterogeneous properties to reproduce the observations.
Right.
And it doesn't say whether the dynamic weakening is occurring or not, right? It's just like to reproduce the observation, we don't even need to resort to more complexity. We kind of resort to the complexity in the frictional heterogeneity, heterogeneous frictional property itself.
Right. Thank you.
Yeah, I hope that's clear. So actually it's connects well to some of the points I want to make here. So this kind of models are increasingly popular. So I've been also kind of leading some of the benchmark work for kind of verifying these kind of numerical models that in a community initiative is supported by SCIC. So we have 2D benchmarks. We already report the results in an SRL paper, and we also will have a paper about 3D benchmarks to be submitted to JGR next week. So I think the benefits of this model is that it really provides a self-consistent physics-based framework for simulating the sequences of earthquakes and slow slip. In my view, I think the advantage of these models is that it really accurately resolves the key lengths and timescales, and it rigorously incorporates the dynamic and static stress transfers. It has the potential because it's a cross-scale simulations, a simulation that crosses multiple timescales, so it can effectively connect laboratory, geologic, seismic, geodetic observations across scales. I also would like to point out and maybe wonder that there are indeed still a lot of uncertainties in these models. One is that we are not really kind of talking about the fundamental physical mechanisms for the fracturing or frictional sliding process, because rate and state friction laws is a phenomenological law. Also, the frictional parameters, it may change in space and with strain rate, but we are imposed in these models. And also the sources and forms of heterogeneities are not clearly specified in the models. And we kind of bypass this step to try to kind of already connect different geophysical observables. To me, it's really kind of we need further steps to kind of further advance our understanding of earthquakes by taking the advantage of these models. The first point is that we should test a lot of these model predictions against diverse geophysical observations. And to address the uncertainty in the models, we really have to improve these models with findings from the lab, as well as field observations that can potentially constrain some of the mechanisms, parameters, as well as the sources of heterogeneity. So that actually kind of motivated me to look more into the observational side during my postdoc. So I try to, given the time limit, I'll try to cut short a little bit about what I will say for the geophysical signatures of post-rupture faulting process at Parkfield. So the motivation for this part of the research is really to understand better how earthquake rupture transitions to post-seismic process. So here, this is a plot of showing you the slip during the magnitude 6 earthquake, Parkfield earthquake in 2004, with seismicity plotted here as dots and circles. The earliest post-seismic period of earthquakes is important in general because it's the immediate post-seismic rupture period with the fastest evolution of certainly aseismic strain rates. And it's also a period where we have a diverse range of processes, such as afterslip and aftershock that occur. So in our case study of the 2004 Parkfield earthquake, we try to use the continuous near-field geophysical observations to understand both the shallower and deeper fault zones. So I will try to be brief about the background of the Parkfield earthquake sequence on the San Andreas fault, because Berkeley seismology lab folks have been studying this earthquake and the segment for a while. So this earthquake has really great observational data related to this recent magnitude 6 earthquake in 2004. Our focus here is really to try to understand the early post-seismic processes from tens of seconds to days after the earthquake rupture. And in particular, we want to understand the relation between afterslip and aftershocks in space and time. So the data that's available for us to investigate the process include strong motion records, as well as high rate 1 Hertz GPS solutions. These solutions are derived relative to a far field station. And we know that the 1 Hertz data does not really capture the near source complexity. So high rate 1 Hertz GPS solution is shown on the left. Since we want to understand the processes that happen after the arrest of the earthquake, we consider 90 seconds as the end of the cold-seismic period to start our investigation of the early post-seismic phase. So maybe the most important part in our paper is about the data that we have kind of processed and massaged to investigate our process. So what's shown here on the left, we have this GPS. These are the observations from highway GPS. So we have highway GPS for the cold seismic phase during this earthquake. And for the post-seismic phase, we have continuous 1 Hertz records for 7 days before and after the earthquake. And we have done sidereal filtering to try to reduce the noise of the periods of 1 minute to 1 hour, which will be crucial for post-seismic studies. We have daily GPS solutions, and we have do some kind of, we do the removal of the interseismic trends so that we can combine the two solutions to construct a continuous post-seismic time series of seconds to days. So there's a lot of things that it seems that we can kind of uncover in these kind of post-seismic GPS time series. Here, we kind of show the fault parallel components versus the fault normal components in panels B and C. So in general, we can note that the future geodetic data, which are shown with logarithmic scales in these two figures, we can reveal continuous transient fault motion that are invisible to seismic data. So in particular, we note several distinct features, distinct signals related in the fault parallel and fault normal directions. So first, we can see there are characteristic logarithmic post-seismic signals in the fault parallel direction. And in the fault normal direction, there seems to be a bit more complexities. One is that we can notice that there are localized fault normal only signals that occur over 2 to 10 minutes in the fault normal directions at 2 stations and possibly 3 stations. And there are also fault normal only signals around 3 to 5 hours, which is actually associated with GPS time data that has a larger noise. So that's the period between 3 and 5 hours. So we ignore these periods, even though they would introduce some artifacts in our fault slip models, but we really kind of focus our attention on some of the earlier and the later periods. I think, yes, so for the co-seismic and early post-seismic periods, if you look at the map view of the displacement during the co-seismic, early post-seismic periods, there are some conclusions people have already studied in a series of previous studies. So for the co-seismic period, we can see that there is generally a characteristic pattern of the strike slip surface deformation pattern associated with the strike slip earthquake. For post-seismic periods, we plot the displacement vector associated corresponding to 10 minutes up to 7 days. As we can see, there are considerable variability in these displacement vectors, indicating there's more complex processes going on throughout the early post-seismic periods. From earlier studies, we know that the seismicity at depths already indicates that there are 2 faults that are involved, not just the San Andreas fault, but also the southwest fracture zone to the southwest of the San Andreas fault, which is suggested to host the earthquake rupture during the Parkfield earthquake. And those 2 faults likely intersect at the depths of 6 kilometers, as seen by the seismicity. If we plot the fault parallel velocity as a function of the distance across the fault, we can see for the co-seismic period, there's a characteristic profile of deformation from which we can see that the earthquake slip really occurs between these 2 stations. Therefore, it occurred on the southwest fracture zone. Similarly, if we look at post-seismic periods, and this kind of characteristic displacement profile evolves in space, meaning that the slip on the southwest fracture zone in the post-seismic period later on evolves and migrates to the San Andreas fault over the period of 3 to 5 days. And this is found in the previous study by Murray and Ombai. So we use these time series data recorded by high-rate GPS in the early post-seismic period, and we can construct a history of the fault slip evolution using finite fault inversions. So I will briefly introduce our ingredients that we use realistic geometry for the southwest fracture zone fault to invert for co-seismic earlier post-seismic periods. In terms of elastic structure, we consider different 1D layered models across the San Andreas fault. For inversion, we use a relatively simple method that we can obtain maximum a posterior slip models and full covariance matrix with no a priori constraints on rake angle and slip positivity. And note that we also have a relatively large resolution length scale, 3 to 4 kilometers, which we impose at the spatial correlation in our slip models. The nice thing about this simple model is that we can derive semi-analytical solutions for the slip models and its variance covariance matrix. But the caveat the caveat here is that because we don't impose slip positivity or the specific rake angle, so the resulting model has larger uncertainties, but we can interpret the model more as best fitting models. And by using the simple model, we can say that we favor the weight of data in inferring qualitative source behavior over time. Certainly, we have more sophisticated methods to kind of derive models with higher resolution. But as I will show later, seems like even with such a simple model, we can get to understand some qualitative fault behavior with time, how the fault changes with time. So what's shown in the top is the fault slip distribution during the coseismic period. We can see that with slip in color, and it basically resolves two main slip patches, and they're generally spread out because we have a spatial resolution of slip models that is 3 to 4 kilometers. So we should view these slip models as a spatially filtered version of what actually happened on the faults. So we do that for several time periods, 5 minutes after the earthquake, half an hour after the earthquake. So in these early periods, we can see earliest afterslip occurs above the coseismic ruptured zone. And interestingly, some of the afterslip already shows a spatially complementary pattern with coseismic slip. Although it's the overlap areas must have been kind of smoothed out because of our lower spatial resolution. On top of that, we plot the aftershocks in those corresponding time periods. For the later periods, 8 hours or 24 hours after the earthquake, we can also derive the cumulative slip on the fault throughout these periods and plot that along with seismicity. So in general, we can examine the spatial patterns of fault slip model and seismicity, but I find that to be difficult because of the different resolutions of seismic and geodetic inferences, right? So the strategy I adopted, actually for these coseismic slip models and post-seismic models, one thing that we can certainly do is that we can use these slip models to calculate Coulomb stress changes, right? So that's one thing that we can calculate the distribution of Coulomb failure stress change due to the coseismic rupture. And where earthquake has occurred, the Coulomb stress tend to decrease. Outside the coseismic slip zone, stress change is positive, right? So we can do that focusing on the first 30 minutes after the earthquake rupture and do that for 5 minutes, 10 minutes, 30 minutes after the earthquake. As I mentioned earlier, that it's generally hard to compare the spatial patterns of seismicity and geodetically inferred fault slip. So my strategy here, especially in the case where there are complicated local stress changes, right? My strategy here is to really kind of compare these different observables over a larger fault, averaged over larger fault areas. So here we have focused on the shallow fault areas outlined here as R1. Within the shallow of R1, we compare afterslip that's averaged over large areas. We can look at how afterslip changes as a function of logarithmic time. We compare that with aftershock moment rate, the rate of aftershock, and as well as the afterslip induced stress change histories. So here I would just kind of list some of the main conclusions that we have derived after such a comparison. One is that afterslip is geodetically detectable after 2 minutes after the Parkfield earthquake. We notice there's some slip reversal that's required by the inversion around the time 5 to 10 minutes. This is because we notice the initial increase and later diminishing of localized fault normal motion at least the 2 stations. We have ruled out the polar elastic rebound due to inconsistent spatial patterns of deformation. And we interpret this slip reversal as potentially due to the dynamic overshoot of the earthquake rupture within a complex fault zone. The net and other features include anomalous period and 3 to 5 hours that could be due to GPS noise or other fault zone processes that we are yet to identify. And the overall seismicity rate in the early periods, as shown maybe here, is reduced compared to the Omori prediction shown by the red dashed line. we interpret that as the effect of the coseismic stress release, reducing the overall early aftershock rates. And then afterslip, when we compare the stress change history with aftershock rates, we notice that this negative and positive stressing rates are somehow appears to correlate with the absence and increase in seismicity, at least in the earlier post-seismic period. With the later periods, harder to compare because of larger uncertainties. And from that, we interpret that the evolving early afterslip likely drives the short-term variation in early aftershocks. We also did the similar comparison for the deeper fault areas, and we're just going to summarize our conclusions here. If we compare shallow and deeper fault zone, the shallow areas shows a largely logarithmic displacement behavior. So we suggest that the velocity strengthening frictional properties should be the same between the earliest and later post-seismic period, for which there are already several studies focusing on the later seismic periods. Deeper fault areas to me, it seems there is some delayed or weak onset of afterslip and aftershocks, including some periods that is likely affected by higher noise. And the absence of early afterslip and aftershocks could be due to a temporary coseismic rupture down dip. And if we look at the later accelerated onset of afterslip, the accelerated increase in slip may suggest that the effective frictional parameters may depend on time because of a dependency on slip rates. So from that, I guess I'll just put my conclusions here. Several important conclusions from this study. One is from this study, we can resolve the complex aseismic and seismic observations associated with the post-seismic phase of the Parkfield earthquake in the early post-seismic period. And we can infer some potentially depth-dependent aseismic seismic behavior. Here, the roles of aseismic slip and structure seems to be important in seismicity evolution. We suggest that early aftershocks are likely modulated by evolving aseismic fault slip. So the conclusions for revisiting Parkfield is that we resolve complexities in this co-seismic to post-seismic transition of the Parkfield event. There's still some unknowns due to data noise, but high-rate geodetic and seismological observations provides an expanded observation window into fault zone dynamics. So I will leave the last slide here. This essentially summarizes the topics that we've covered, including seismic quiescence on major San Andreas faults, transient aseismic slip on San Jacinto fault, and the early post-seismic studies for the Parkfield segment. And I'll be happy to take some questions.
Thanks very much, Junle. I have a question. I'm really intrigued by this backslip. So maybe you could you show on the cross section spatially where do you think the backslip is occurring? Is it like 3 minutes after, or?
Maybe first we can look at the time series data here. So I think we have the feature. So essentially, these backslip really can be tracked back to the fault normal signals as seen here at Hogs and CARH. Those two stations are closest to the fault. So the time period is about between 2 minutes and 10 minutes. We see that there is a fault normal movement, especially at Hogs, and then goes down. And we can see the movements at heterogeneous, CARH, and potentially another station, but these two are clearly showing that. And when we do the inversion with the data sets, and these kind of fault normal movements will be mapped into initially positive slip, which then diminishes from 5 to 10 minutes. So that's how we interpret the backslip occurred. It's really down to the signals at these two stations. And we make the argument that because it's only showing the fault normal movement, and those stations are closest to the fault. So we do think, and also the signal to noise ratio is high at these stations. So we think it's really related to physical signals rather than artifacts.
I don't remember where all the stations are, but I think Carr Hill's in the center.
Yeah, Carr Hill is the one that's actually in the center, right?
And hogs, I don't remember.
Yeah, so CARH is the one crucial station that from which we can see that the slip has migrated from southwest fracture zone to San Andreas fault. It's also the station that shows this for normal signals between 2 and 10 minutes.
And hogs is actually away from the fault, but it's also towards the center. Is there any microseismicity? That I don't think it could be pulled out, but it'd be interesting if there's any microseismicity where you could actually see reverse polarity.
In terms of microseismicity, we compared that with the catalog by Zhigang Pen, which is a kind of template matching based size catalog, right? It's much more complete than the Northern California seismic network.
Yeah.
So we can compare that in terms of the moment, like I computed the aftershock rates and aftershock moment rate and how it changes with time. If there is a major large early aftershock, then it will show up in the moment rate. Maybe, I don't know, there are some kind of fluctuation.
You'd expect to see some negative correlations. Like there's some significant negative correlations in the template matching. I think that's what you'd see.
We interpret that the absence of early aftershocks on the shallow faults to be due to this reverse slip. There's a gap in the seismicity early on, and there's also increase later on. I think the back slip actually increases the stress change. So this bump here is actually correspond to the back slip, and it kind of correlates with some increased seismicity after the initial quiescence. I think the limitation here is that the geodetically estimated fault slip is kind of, it has large spatial resolution. So we are doing spatially average comparison, but maybe there's some local, more complex process going on.
Actually, let me just ask one follow-up question. So when you're doing the template matching, do you allow for negative? Do you consider the negative correlations? Do you keep them or do you throw them out?
To be clear, I didn't do template matching of aftershocks. I just used the aftershock catalog from Pen and Zhao study.
Okay.
So I use other people's catalog.
I wonder what they do.
When they did that, they were not aware of the complexity. Yeah, I'm not sure.
You mean the waveform?
Yeah, the waveforms would be reversed.
I see. Because the back slip.
Yeah.
What is the mechanism?
Yeah.
As to whether they can resolve some kind of mechanism, they say no, they cannot do that. But I'm not sure whether you can do that through different ways in the template.
Yeah, probably not the details in the mechanism, but the mechanisms are very structurally controlled here. You know, they're near vertical strike slip. So you'd see a reversal in polarity probably at all stations if there was a seismic event associated with backslip. That method they're using, that would produce negative correlations. So if they don't keep the negative correlations, then those events may not enter into the catalog.
I think I can follow up with them to see.
Yeah, it's really an interesting observation you have.
I think, yes, initially, I guess it's not very physical to have these backwards. I mean, in some sense, I wasn't expecting to have backward slip, but there are some observations regarding backward aftershocks with the reverse focal mechanism. Or maybe backward creep. So at least in these situations within right after the rupture within geometrically complex fault zones, it's a possibility. I have not done more dynamic simulations to see the feasibility of that.
For the Tohoku earthquake, people suggested that as well. And Naoki Uchida looked for anti-repeaters and didn't find any.
So in the chat, Yifeng says that there are some repeating earthquakes with high negative cross correlations in the ridge crest sequence.
Suggests the totally opposite focal mechanism.
Yeah. Yeah, I remember Dave Shelley found evidence of that at Mammoth.
I don't think so. I remember I just put it.
Yeah, it's very interesting. Any other questions for Junle?
I have a question. I wonder, like, in what kind of circumstance the larger earthquake may nucleate in the shallow depths? I wonder, in your modeling, it seems like a larger earthquake nucleate from the deep area near the brittle ductile transition zone. But in the ridge crest earthquake, the hypocenter is really shallow, around 2 to 3 kilometer depths.
Mm-hmm. Yeah, it's a really interesting question. I mean, just from the thinking from the models in general, if we have designed a seismogenic zone that has surrounded by velocity strengthening areas, generally earthquake tends to nucleate deeper because of the higher loading. Unless there's some kind of heterogeneity or unless it's at the lateral boundaries of these frictional areas, sometimes they nucleate at lateral boundaries. So it could, maybe that could be slightly shallower than the down dip transition. But in reality, sometimes, I don't know, for example, the Ridgecrest earthquake, it's not clear that where they nucleate, it's nucleated at, say, at the base, whether there is actually the transition of seismogenic zone at shallow depths to the creeping zone, right? Or we may not know about the prior slip history to know where the stressing on the fault is higher or not, right? So I guess our models in general are simple in that it has system-sized ruptures actually kind of removes a lot of stress heterogeneity right after the earthquake. So maybe in some more complicated models, if you have partial ruptures, if you have some kind of events of different sizes, maybe it will make some other locations other than the down dip transition to be favorable for the nucleation of some events.
Well, thank you very much, Junle, for a really stimulating seminar.
Thank you, everyone.
You know, I had another question. What I was wondering is, are there any events that arrest? So, you know, do you have a distribution of earthquake sizes? Then does the scaling, like the area scaling, does that agree with the empirical scaling laws?
I actually have some kind of event distribution for these two models. I plotted some time ago.
Oh yeah, okay.
So this is the two models,
from
very simple models that use to study the effect of how depth limit of larger and small events. Then I plot the frequency size distribution for the events produced in the models. So what you can see, this is far from the reality, I think. So that's why I kind of plotted, and I think, oh, that's interesting because the B values in these two plots, one is 1, kind of a more closer to some of the observed values. The other is very small B value because there are not much seismicity, right? Qualitative difference kind of makes sense to me. So from that, I think I had some kind of ideas about, oh, maybe the dynamic weakening, the kind of effects from larger earthquake can affect the frequency size distribution. But these are I think I'll only have maybe, even for the first model, only have several hundred events. Yeah,
I was just really interested in how, in that one model where you put a rough initial friction law beneath the main patch, you had your A minus B, that was heterogeneous, and when you got breakaway rupture, it extended into that zone. So the rupture was significantly wider down dip than one would
expected from,
based on the seismogenic zone.
Yeah, in some sense, it's kind of ruptured down to the depths of the seismicity. It's an example where the geodetically estimated locking depths can actually is not a good estimate on the extent of earthquakes, which is contrary to these models that presented. So I guess it's interesting numerical experiments. I'm thinking like these different scenarios can actually produce very different observations and maybe the interpretations for the hazard.
Yeah, there could be. All right, well, thank you very much.